Let's now discuss the different types in Solidity to a bit more detail. Starting off with the Boolean type. Boolean types are declared using the bool keyword, and they can really have only two possible values, true or false. There are 5 operators that can operate on Boolean types: the logical negation or not operator, the equality operator, inequality, and finally the and or operators, or also known as logical conjunction and logical disjunction operators. The or and logical conjunction, logical disjunction operators apply what are known as the short circuiting rules that you may be familiar with from other languages. This means that, for example, in an expression that uses the logical disjunction or operator, if there are two booleans, let's say x or y, if x evaluates to true, then the boolean y will not be evaluated at all, even if it may have side effects. This is because the expression already evaluates to true, and there is no need for the second boolean to be evaluated at all. And similarly, this applies to the AND operator, logical conjunction, as well. So if there are two booleans that have this operator, let's say x and y, and if x happens to be false, then we know that the expression finally will evaluate to false, and so there is no reason really for the compiler to evaluate y, because the result is already known to be false. From a security perspective, booleans are used significantly in smart contract functions for various conditionals and evaluations of expressions. So this affects the control flow, and specifically when it comes to certain checks, access control checks. In some cases, there have been cases where booleans have been used and the wrong operator has been used in those checks. So for example, using the not or logical disjunction instead of logical conjunction can have big implications to how that particular expression evaluates, and that check, the access control check or whatever that might be, might not be effective at all as intended by the specification. So these are again something to be considered, pay attention to when you are looking at booleans and the operators that evaluate that operate on the booleans in smart contracts. Now let's look at integer types. Integer types are again very common in Solidity and really in any programming language. There are unsigned and signed integers of various sizes in Solidity. They use the uint or int keywords and come in sizes from 8 bits all the way to the word size of 256 bits. So you'll see declarations of unsigned integers or integers, signed integers, in the form of uint 8 all the way to uint 256, or int 8 all the way to int 256. There are various operators for integer types. There are different categories that we saw in the EVM instruction set: arithmetic operators, comparative operators, bit operators, and shift operators. And from a security perspective, given that integer variables are vastly used in Solidity contracts, they really affect the data flow of the contract logic. And specifically, there is an aspect of integers that becomes really security critical, which is that of underflow and overflow. We'll take a look at what that means in the next slide. Integer arithmetic is really arithmetic that operates on integer operands, operands of signed integers or unsigned integers. And integers in Solidity, like in any other language, are really restricted to a certain range of values. So for example, if you have uint 256, then the range of that variable is from a value of 0 to 2 power 256 minus 1. And if there is any operation on that variable of let's say uint 256 type that forces it to go beyond this range, then it leads to what is known as an overflow or an underflow. And this really causes wrapping. So in the case of uint 256, let's say that the value of one of those uint 256 variables was the maximum value of that range, which is 2 power 256 minus 1. And if the contract logic incremented it by 1 more, then that integer value would overflow, it would wrap to the other side of the range and would become 0. Similarly, an underflow, let's say in the case of this variable, if the value was 0, and if the logic decremented it by 1 more, then it would again cause wrapping to the other end of the range, and the value of that variable would now be 2 power 256 minus 1. So as you can imagine, this can have significant unintended side effects when it comes to the integer values used in that logic. And there have been numerous cases of such integer values being overflowed or underflowed, leading to really huge exploits, vulnerabilities in a security perspective. And this is something that is really, really critical when it comes to the security of integers, specifically in the smart contracts. And so for addressing this specific aspect, in versions of Solidity below 0.8.0, so all the versions until 0.8.0, the best practice was really to use the safe math libraries from OpenZeppelin that made operating on integer variables safe with respect to overflows and underflows. And Solidity itself, as a language, recognized this aspect of security and introduced in version 0.8.0 default overflow and underflow checks for integers. So now in contracts that are written with the compiler version 0.8.0 and above, one can actually switch between the default checked arithmetic that checks for underflows and overflows and causes exceptions when that happens, versus unchecked arithmetic, where the programmer or the developer really asserts that for the expressions used in that unchecked arithmetic, there is really no way or no cause for concern when it comes to overflows and underflows. So all the default underlying checks in the language, in the compiler itself, should be disabled. This is something to be paid attention to, really a critical aspect of smart contract security. So when you're looking at smart contracts, do pay attention to the Solidity compiler version that was used. If it is below 0.8.0, then really there should be the use of safe math from OpenZeppelin or some of the other equivalents that make sure that the integers don't overflow and underflow and cause security vulnerabilities. And if the compiler version is 0.8.0 or beyond, then one should pay attention to any expressions, integer expressions that are using unchecked blocks to make sure that those don't have any overflows or underflows. Let's talk now a bit about fixed point arithmetic and the support for it in Solidity. Conceptually, you would have seen this in other languages as well. For numbers that have an integer part and a fractional part, the location or the position of the decimal point indicates if it is fixed or floating. If that position or location of the decimal point can change for that type, then it is referred to as a floating point type. But if that position is fixed for all variables of that type, then it is known as fixed point arithmetic. And in the case of solidity, these can be declared but really cannot be assigned to or from. The keywords are fixed and ufixed for signed and unsigned fixed point values. There's no real support, like I mentioned, in Solidity, and for any use of fixed point arithmetic, one has to depend on some of the libraries such as DS Math, PRB Math, and some of the others available. Let's now talk a bit more about a type that is specific to Solidity and very specific to Ethereum and really critical to security. This is the address type. The address type in Solidity really refers to the underlying Ethereum account address, the externally owned account or the contract account that we discussed in good detail in the Ethereum module. Now, this is different from the addresses that you might have encountered in other programming languages such as C and C++, where they really refer to the variable's memory address when you're dealing with pointers or references. But here, address signifies something very different, and that's really the account address. These address types are 20 bytes in size, because that is really the size of the Ethereum address as we discussed earlier. And they come in two types. They can be plain address types, or they can have a payable specifier and referred to as an address payable type, where it indicates that this address type can receive Ether. There are different operators that operate on address types, such as shown here. There are conversions that can be performed on address types. Some of them are implicit, some of them are explicit. So for converting address payable types to address types, that can be an implicit conversion because it is safe. Whereas the other way around, where an address type is converted to an address payable type, that should be an explicit conversion because now this address becomes capable of receiving Ether. And from a security perspective, you can imagine how address types play a critical role in contracts. These addresses are used in different types of access control. Some addresses may be considered as more privileged than the others in the context of the contract logic. Addresses can also hold Ether balances, token balances. So using the right addresses in the right places and making sure that the correct access control logic or the balances accounting logic is applied on these addresses becomes very critical from a security perspective to make sure there are no undefined behavior or unintended side effects leading to security vulnerabilities. Address types have different members that can give you different aspects of the underlying address type. There is the balance that gives you the balance of that address in way. There is the code that gives you the code at that address. There is code hash that gives you the hash of the code at that address. And we talked about several of these in the context of the EVM instruction set as well. There are also the transfer and send members that are applicable to the address payable types. And these primitives, as we talked about earlier in the context of the receiver fallback functions, they make calls to the addresses that are specified by supplying a limited gas stipend of only 2300 gas units. And this is not adjustable. This is something hard-coded in Solidity. And this is really to address the category of reentrancy attacks that is possible on addresses. We'll take a look at the reentrancy aspect later on in the security modules, but something to be kept in mind for now. There are also members of call, delegate call, and static call that can be applied on address types. These are really used to make low-level calls to the specific address that is specified. We talked about some of these calls in the context of the underlying instructions, the call, delegate call, and the static call instructions, where we talked about how the callee account, in the case of delegate call, executes with its logic but with the state of the caller account. And similarly, in the case of static call, we talked about how the callee contract address can access the state but cannot modify the state. So as you can imagine, these address members play a huge role when it comes to the security aspects, because they deal with the balances, looking at the code hash, the reentrancy aspects of send and transfer, making external calls using call, delegate call, static call, which are really critical when it comes to the trustworthiness of the contracts that are being called at these addresses. Let's now take a further look at the transfer primitive that can be applied on addresses. Like we just discussed, the transfer function is used for transferring ether to the destination address. And this transfer really triggers the receive function or the fallback function of the target contract, as we discussed earlier. And this comes by default supplied with 2300 gas subsidy. This is a fixed amount, cannot be changed, and if the target contract, the receive or the fallback functions of the target contract uses more than 2300 gas, then it fails, the transaction fails, it reverts, and there is an exception that is caused, and this is really by design. So from a security perspective, this primitive affects reentrancy. Talk a bit more about that later on. And this is really a primitive that was introduced to mitigate the concept of reentrancy, where the target contract, if it is untrusted, could potentially call back into the caller contract and really lead to unintended or undesired behavior that could affect token balances or other contract logic in a very critical way. And again, from a security perspective, there is the notion of 2300 gas subsidy, which is fixed for transfers. This gas assumption is critical when you look at how contracts use transfer and whether that transaction could fail and revert and lead to undefined behavior. Similar to transfer, there is the send primitive or the send function in Solidity. This is somewhat of a lower level counterpart for transfer. This again is used for ether transfers. It triggers the same receiver fallback functions like transfer. It also has the 2300 gas subsidy, but it does not result in a failure if the target contract uses more than 2300 gas. Unlike transfer, where it leads to a failure and revert, in the case of send, it does not revert, but it just sends back a Boolean return value that indicates a failure or a false Boolean value in the case of failure. So if this primitive, the send primitive, is used to transfer value, then from a security perspective, it means that the return value of that send primitive must be checked by the caller to make sure that the transfer happened successfully or not, depending on what was returned. So again, from a security perspective, the send primitive affects reentrancy, which is really why the send primitive was introduced as a mitigation in Solidity. There is also the gas assumption, the 2300 subsidy aspect that affects security. And then finally, the return value check that is critical, and that is something different from its transfer counterpart. Let's talk about how external calls are made from Solidity and the security implications of such calls. There are really three primitives that we touched upon earlier. These are the call, delegate call, and static call. These are used to interface with contracts that do not adhere to the API or where the developer wants more direct control over such calls. They all take single bytes memory parameter. They return the success condition as a Boolean, and they return data in a bytes memory. They can also use functions such as ABI encode, encode pat, encode with selector, encode with signature to encode structured data as part of the arguments. They can also use gas and value modifiers to specify the amount of gas and ether for these calls. This is really applicable for the call primitive, but not delegate call or static call. So to summarize, the delegate call is used where the caller contract wants to use the logic specified by the callee contract, but with the state and other aspects of the caller contract itself. So while the code of the given address is used, all other aspects such as storage, balance, message sender are taken from the current caller contract. And the purpose of this delegate call is really to enable use cases such as libraries or proxy upgradability that we'll talk about later, where the logic code is stored in the callee contract, but that operates on the state of the caller contract. And static call is used where we want the called function in the callee contract to look at or to read the state of the caller contract, but not modify it in any way. So as you can imagine, the use of external calls have different types of security implications. These are really low-level calls that should be avoided in most cases unless absolutely required and there are no alternatives available, because these are calling out to external contracts that may be untrusted in the context of the current application's threat model or trust model. These contracts, external contracts, could result in undefined behavior, use more gas than expected, also cause reentrancies to the caller contract, and might also return failures where if the return value is not checked, could result in undefined behavior as well. Let's now move on to a different type, the contract type. Every contract that's declared is its own type. And these contract types can be explicitly converted to and from address types because that is really what they represent underneath. These contract types do not have any operators supported, and the only members of these types are external functions declared in the contract along with any state variables whose visibility is. The next type is something known as the bytes arrays. As you can guess, these types are used to store arrays of raw bytes. There are two kinds here. If we know what the size of the byte array is going to be in advance, then we can use what are known as fixed size byte arrays. They come in 32 kinds. Bytes 1 for storing 1 byte, bytes 2 for 2, all the way to bytes 32 for storing 32 bytes, which is really the full word size in the context of EVM. If we do not know the fixed size in advance, then we can use the alternative, which is indicated by byte followed by the square brackets. This type is good for storing byte arrays where we do not know the fixed size in advance, but due to padding rules of EVM, it wastes 31 bytes of space for every element that is stored in it. So if we have a choice, then it's better to use the bytes type instead of the byte type for these byte arrays. And this is something that you will commonly come across in smart contracts for storing raw bytes, example in the case of hashes. The next type is what are known as literals. This is something that you would have come across in other programming languages as well. Solidity supports 5 types of literals: address types, rational integers, strings, Unicode, and hexadecimals. The address literals are hexadecimal literals that pass the address checksum test. Recall that Ethereum addresses are 20 bytes in length. So in the case of the hexadecimal address representation, every nibble in that address, so half a byte, is represented by a hexadecimal character. So this results in the address literal having 40 characters, 2 for every byte. And these should pass the checksum test. The checksum is something that has been introduced in EIP 55 to make sure that there are no typographical errors when you're using addresses in the context of Ethereum. This is a mixed case address checksum, and I would encourage you to take a look at this EIP to understand how that works. Rational literals and integer literals are also supported. Integer literals have sequence of numbers in the 0 to 9 range. The decimal fraction literals are formed by using a decimal point with at least one number on each side. Scientific notation is supported, where the base can have fractions and the exponent cannot. Underscores can be used to separate these digits. This is really used to help with readability and do not have any significance semantically. String literals are supported, and these are written with either double quotes or single quotes. They can only contain printable ASCII characters and a set of escape characters. Unicode literals are supported. They have to be prefixed with the keyword Unicode, can contain any UTF-8 sequence. And finally, the hexadecimal literals are also supported. These are hexadecimal digits prefixed with the keyword hex, enclosed in double or single quotes. And the usage of all these literals is in the context of constants, and you will see a lot of these literals used within smart contracts. The next type is enums. This is something we talked about earlier. Enums are a way to create user-defined types in Solidity. They can have members anywhere from 1 member all the way to a maximum of 256 members. And the default value of an enum is that of the first member. And this is something that you see sometimes in smart contracts, where enums are used to represent the names of the various states within the context of the contract logic, or the transitions in some cases. So this is something that really helps to improve readability instead of using the underlying integers that the enums really represent. Function types are types used to indicate that variables represent actual functions. These variables can be used just like any other variables. They can be assigned from functions because they are of the function type, and they can be sent as arguments to other functions. They can be also used to return values from other functions. They come in 2 types, internal and external. Internal functions can only be called inside the current contract. External functions consist of an address of the contract where they're relevant, and a function signature along with it, and they can be passed and returned from external function calls. The usage of function types is somewhat minimal in most of the common smart contracts that you would see. Let's now talk about the concept of data location. We talked about value types and reference types. Reference types, which is the structs, arrays, and mappings in Solidity, allow for a specification of their data location. So this is an additional annotation, and it indicates where that reference type variable is stored. And there are really 3 locations: memory, storage, call data. Recall that these are 3 out of the 4 locations that an EVM supports besides a stack. And these data locations affect the lifetime or the scope and persistence of the variables stored in those locations. Memory indicates that the lifetime is limited to that external function call. Storage location indicates that the lifetime extends to that whole contract, and this is also the location where state variables are stored, if you recall. Call data is a non-modifiable, non-persistent area where function arguments are stored. This is required for parameters of external functions, but can also be used for other variables. And this data location annotation really impacts the scope of the variables that use this notation. And from a security perspective, this affects the persistence of those variables. The data location annotation we just talked about not only affects the persistency of those variables, the scope in which they are relevant, but it also affects what are known as assignment semantics. And in the context of Solidity, what this means is during an assignment using such variables, is a copy of that variable being created, or is simply a reference being created to the existing variable. So in Solidity, storage and memory assignments always creates an independent copy. Memory to memory assignments only create references. Similarly, storage to storage assignments create only a reference, and all other variants create a copy. And from a security perspective, how this impacts the semantics is if a copy were to be created because of these assignment rules, then any modifications to the copy really affects only the copy and not the original variable from where it was copied. But if a reference was created, in the case of memory assignments or storage assignments, then the new variable, modifications to that, affect the original variable because both of them are just different names pointing to the same underlying variable data. So this becomes important when you analyze programs and notice what the data locations are for those reference types, because there's a big difference if modifications are being made to the copy versus a reference. Array types. These array types are something that are very common in most programming languages, and you would be familiar with them already. In the case of Solidity, they come in two types. They can be static arrays, where the length is or the size of the array is known at compile time, or they can have a dynamic size. They are formally represented as shown here, T of k, which is a static array of size or length k. And if we do not know the size k, then it's an empty set of square brackets, in which case it indicates that it is a dynamic array. The elements of these arrays can be of any type that is supported by Solidity. The indices that are used with these arrays are zero based, which means that the first array element is stored as t of 0, not t of 1. And if these arrays are accessed by the logic past their length, then Solidity automatically reverts that access and creates an exception. And this really causes a failing assertion in the context of the contract doing such an access. So from a security perspective, arrays are very commonly used in smart contracts. The things to pay attention to are to check if the correct index is being used, especially in the context of indices being zero based, and to check if arrays have an off by one error, where they're being accessed either beyond or below their supported indices, in which case such an access could lead to an exception and the transaction would revert. The other aspect to keep in mind with arrays is if the length of the array that is being accessed is really long, and if the types are complicated underneath, then the amount of gas that is used for the processing of such arrays could end up in what is known as a denial of service attack, where those transactions revert because not enough gas can be supplied as part of the transaction. So you would end up with no processing really happening because the transaction would revert. The members that are supported for array types, there are 4 of them. There is the length, push, push of x, and pop. These are again very obvious. The length returns the number of elements in the array. Push, it appends a 0 initialized element at the end of the array and it returns a reference to that element. Push of x appends the specified element x to the end of the array and it returns nothing. Pop, on the other hand, removes an element from the end of the array and implicitly calls delete on that removed element. These are again very similar to other programming languages that you would be familiar with. And from a security perspective, the things to be paid attention to are again the length of the array that is being considered in the context of indices being 0 based, and any off by 1 aspects of accesses that lead to failing assertions. Push and pop semantics to make sure they're being considered correctly in the context of the smart contract logic. Let's now talk about 2 other types supported by Solidity, bytes and string. Bytes are used to store arbitrary byte data of arbitrary length. And recall that if we know beforehand the size of the byte array, then we can use the fixed size byte arrays indicated by bytes 1, bytes 2, all the way to bytes 32 to store those number of bytes within those types. But if we do not know what the size is beforehand, then we can use the bytes type. And even there we have a choice of bytes or the byte array we talked about earlier. And recall that the byte array uses 31 bytes of padding for every element stored and leads to wastage of that space. So it's preferable to use bytes over the byte array. And string type is equivalent to the bytes type, except that it does not allow accessing the length of the string and the index of a particular byte in that string. So it does not have those members. So that is the big difference between these 2 types. And Solidity does not yet have inbuilt string manipulation functions, but there are third-party string libraries that one can use. Memory arrays. Memory arrays are really arrays that are created in memory. They can have dynamic length and can be created using the new operator. But as opposed to storage arrays, the difference here is that it's not possible to resize these memory arrays. So the push member functions are not available for such memory arrays. So the options are for the developer to either calculate the required size in advance and use that appropriately while creation of these arrays, or create a new array, memory array, and copy every element of the older memory array into the new memory array. An example usage is shown here.